So, hello dear students, good evening to all of you. How are you? So, here we are with our lecture number 9 on gravitation. Till now, we have covered 8 lecture of it, and most of the topic has been covered. Only one or two, one or two topics are remaining in this chapter after this lecture. Okay, so let me get started with it. Huh? How are you guys doing? Good or great? Tell me, every one of you. Priyanka is here, Mamata is here, Mahesh is here, Hashira, every one of you. Are you being good or great? So, what is your mood today? Out of 10, you have to mark it, है ना? 1 to 10. 1 is very bad, 10 is very, very good. So, let me start with me. Okay. So, today my mood is 10. What about you guys? No one has responded yet, which means nobody has a mood today. Not even the good mood or bad mood, huh? So, whatever. Okay, we have Vikas, which has a very good mood here. Only the Vikas. Samsung Lab 2 has also gives a thumbs up. Okay, only two of you are having a great mood, na? So you are like me for today. So best wishes for the others because what we can do. Bharat is also here. Okay. Okay, then we three or four that have a great mood. Start with the great mood, and I will pray to the God that others will gain also this kind of mood. so, so here we are now. Let me just take the pen of it. Yeah. So today we are going to learn basically about the Kepler's law of planetary motion. In the previous lecture also we have covered some part of it, but what we will do today, we will revise it and then proceed on the further laws. Okay, then we will cover the rest of the lecture. Okay, and firstly we will recall some concept. The recall part is same because there is nothing much to conclude here. The gravitational potential energy, it is the energy acquired by a body due to the change in position, and which is given by U is equals to minus of gm1 m2 by r. Okay. Orbital velocity we have when anything orbit orbit around a heavier object, that velocity is termed as the orbital velocity. So the velocity at which a body revolves around the other body, the heavier body. Okay. So for Earth, if we would say this velocity is root g me over ra, which means mass of Earth divided by the radius of Earth. You can see in this expression, it is independent of the mass of the body which is revolving. Like for our Earth, the moon is revolving around our Earth. So this velocity is independent of the mass of moon. Or we have lots of satellite in our Earth. orbits which revolves around the earth. So all the velocity, all the satellite that we have is the mass of the satellite would not come into the expression of the orbital velocity. So if you just launch a 10 gram of satellite or you will launch a ton of satellite, you will have to gain the same velocity. Same goes for the escape velocity, but it is greater than the orbital velocity. You can see in the expression. And it is a velocity which we require to free a body from the gravitational field of the another body. Okay. So every planet, every mass creates its gravitational field. So if you want to free yourself or any other mass particle from the gravitational field which is created by another mass, that velocity you have to give it a escape velocity. Okay, which is 2 gme over re. Okay, so we have one more guys in the number 10, which is Kiara Manika. So good, very good, Kiara. You have joined the party. Now, the total energy of the satellite moving in the circular orbit. I have derived this expression in the previous lecture, and let me tell you what was that. It is the total energy. Total energy is equals to what? GMEM by 2 RE plus H negative. So this energy is negative. That means this satellite remains in stable equilibrium. It is a stable equilibrium. Okay. And this negative sign of energy also indicate that this satellite is bind with this planet. Okay. So it cannot leave this orbit or change this orbit if anything would not change. But if you just launch a rocket from here and this rocket just hit this satellite, so what will happen? It will gain some kinetic energy. So the path of the satellite would change. Okay. And if this kinetic energy is sufficient enough, if this kinetic energy that is provided by this rocket, kinetic energy is half mv square. If this v is nothing but the escape velocity, so this satellite would escape from this orbit or from the gravitational field of this planet. Okay. Now, so we have also discussed about this, that about 2000 years ago we have Claudius Ptolemy, which has told us that, let me just show it what he has told. He assumed that the earth is at the center of the solar system, and each and every object present in the solar system revolving around the earth. Okay. So this model is also termed as the geocentric model, in which our earth is at center and all other things present in the solar system revolving around the earth in a circular orbit. Even he has assumed that sun is also revolving around the earth in a circular orbit. Got it? So, and this conclusion or this model was accepted widely at that time without any objection. But when the scenario had changed by Aryabhata and Galileo Galilei. So they have made a very keen and fine observation of universe and developed some philosophical theories that we would study. And they have also given the model, like the heliocentric model, the most reliable one of that time, in which we have sun at the center of the solar system, and each and every planet present in this solar system is revolving around the sun. But in this heliocentric model, the orbit in which this planet are revolving is assumed to be the circular one. Got it? And also, the sun is said to be stationary in this. So we cannot say that this heliocentric model is incorrect, was incorrect. No, this is not incorrect. This is incomplete. Okay. Then, then 1000 years later, we had a person named Nicholas Copernicus. I think each and every one of you are aware about this name and heard this name a lot of time. This has also worked on the same model, okay, and developed the fine observation of it. Precisely, he has observed it. Okay. After that, we have this person, which is Tycho Brahe. Okay. So, based on the data collected by from the previous observation or previous model, he has developed a model by himself and named that the geocentric model again. But in this model, what is the feature of this model is he has told us that each and every planet of the solar system is revolving around the sun, revolving around the sun. Okay, in circular orbit. Okay. So in circular orbits are circular here, circular orbit. But what is the thing that is different from the others? It is the fact that our sun is also revolving around the earth. So he has assumed that in geocentric model, the each and every planet present in the solar system is revolving around the sun, but our sun is revolving around the earth in a circular orbit. So this is the geocentric model of circular orbit. So at that time, one of his student working with him, and after the work he has provided, and we name them as Kepler. Okay. Johannes Kepler. So Johannes Kepler was one of the scholar of Tycho Brahe. He has studied all the models provided by the previous physicists or astronomers like Aryabhatta model and Copernicus, Galileo Galilei, and also the Tycho Brahe. The keen observation, the very nearer observation was given by this Tycho Brahe person. Okay. So Copernicus was the scholar of Tycho Brahe. He has studied all the documentation he has provided for this geocentric model, and he has developed, based on that data, he remodified this geocentric model and developed three laws from it. We named them as Kepler's laws of planetary motion. Okay. So in the next slide you will see also the Tycho Brahe has also spent his whole lifetime to record this observation. Okay. And that observation was analyzed by this person, which is Johannes Kepler. Okay. This is the person who is responsible for that. So he has provided us three models. The first one is the, so just a second. Yeah. So the first one here is the laws of orbits, and the second is law of area, and law of period is the third one. But I must tell you that he never numbered them. That if you are talking about the first law provided by Kepler, it should be or it must be the law of orbit. It is not like that, and it is written nowhere. For our assumptions, yeah, for pre-assumed theories, we have developed this, that oh, first law is the law of orbit, second is the law of areas, and third is the law of period. ठीक है? But Johannes Kepler has said nothing about it, that you should put the law of period at number 3 or put the law of areas number 2. ठीक है? Got it? Now, if we talk about the laws of area, law of area is nothing but it tells us about, sorry, law of orbit. It tells us about on which type of trajectory a planet should have when it revolves around the sun. So one thing that has been clear over a decade, since the time period of Kepler has begun. So one thing is very clear from the previous model, that our solar system is not has Earth as the center. Sorry, it has Sun as its center. Okay, and each and every planet of the solar system is revolving around it. But Tycho Brahe has added one thing more spicy in that, which is that the sun is not also not fixed. Sun is also revolving around the Earth. Okay. But in the previous observation, all of the model are based on that particular statement, that if a planet is revolving around the sun in the solar system, it will must take a trajectory which is circular in nature. Okay. But the Johannes Kepler has paid more attention to it, and he came up with a conclusion which is named as law of orbits. He has told us that each and every planet is definitely revolving around the sun. There is no doubt in that. But they are not revolving in a circular path. Oh my goodness. What is that? So which kind of path, which kind of trajectory they are taking? So Johannes Kepler has said that each and every planet is revolving around the sun in a elliptical orbit. Okay, elliptical orbit. I must tell you that circular orbit is the subset of the ellipse or elliptical orbit. Okay. Now, what kind of ellipse will look like? So ellipse will look like this, not like this. It is not to the upscale. I will tell you. So this is the law of orbit. You can see here this trajectory that this point P is taking, which is nothing but Earth, our Earth, and it is revolving around the sun in an elliptical manner, elliptical orbit. So this trajectory is called the ellipse. It is the ellipse. Okay. An ellipse has two center. At center number 1, the sun is present, and here is the another center. So you can read it from the statement that all planets moves in elliptical orbits with the sun situated at one of the foci of the ellipse. And foci is nothing but the plural of focus. So when we have two focus, we do not say that we have two focus. Okay? We will say that this body or this trajectory has foci, which is the plural of focus. Okay? Which means that we have more than one focus here. Okay. So if you again see this, this is how our Earth is revolving around the sun. But in this animation, there is one mistake, that it has shown us that it is moving, the Earth is moving with a constant speed throughout its journey. It is not like that. Okay. And that is the fact we have to study in the next law. This law is clear to everyone? Okay. So from the definition of ellipse, the distance of point P at the trajectory at this point, at this trajectory. If you take any point and you measure the distance of that point from this focus PF1 and this focus PF2 at any point of time, at any point of time. So the sum of the distance PF1 plus PF2 is always come up to be a constant. Okay? So this would always be a constant. This is the property of ellipse. Okay? Got it? Now, the law of area I will tell you. The law of area said that the line joining any planet to the sun, the line joining to the planet with the sun, like in the previous one, this. So this line join this planet to the sun. So what laws of area said that? Laws of area said that the area swept by this volume per unit time, area swept by this line per unit time will be a constant value. Okay? It is like from here to here, from here to here, this line has swept some area. You can see here, this line has swept some area. So this area swept by this line per unit time is a constant quantity. Okay? Is a constant quantity. Got it? Now, you can say that change in area per unit time is the aerial speed. Okay? So, in the second law of area, you can say that the line that joins any planet to the sun sweeps equal areas in equal interval of time, which means if there is a planet, this is the ellipse, this is the common center of ellipse. This is one of the focus at which sun is present. Here we have another planet. From T1, it is here. At time t is equals to T1. And at time t is equals to T2, it is here. So it has swept some of the area. Let's say this area is delta A1. Okay. Here you can say planet is here at t is equals to T3. And at t is equals to T4, it is here. So the area swept by this is this much. Okay. This is the area swept. So if delta T dash, or let's say delta T A, which is T2 minus T1, and delta TB, which is T4 minus T3, are equal, which means delta TA equals to delta TB, then we can say that according to Kepler's law, then delta A1 is equals to delta A2. Okay. Delta A1 by delta T A equals to delta A2 by delta T. Got it? So this is the area swept by this planet. Remains constant. The rate of sweeping the area per unit time remain constant. Okay. And why it is so? Why it is happening? Let me tell you. We all know that We all know that. Just a second, let me change the color of the pen. This is our sun. This is another planet. Okay. It moves here to here to here. Okay. At every point of time, the gravitational pull provided by the Earth is passing through the center of sun, है ना? For this planet is passing through the center of sun. So we can say that the torque about the center of sun, torque about center of sun is equals to 0, because the line of force is passing through the center of rotation or the axis of rotation. Okay. So we know from the previous chapter knowledge, we know that this quantity torque will remain 0. And if torque is 0, we can say that angular momentum is not changing. If angular momentum is not changing, we can say that this L vector, which is nothing but m r cross v, mvr sin theta, है ना? This remains constant. So it is a constant quantity. ठीक है? Let's say let's say just a second. Let me just draw it. Yeah. So let's say this is the sun and this is another planet. At time t, it will at this position. At time t is equals to t1, and at time t is equals to t2, it is here. So it has swept, or let's say not at this point. We will take this point very nearer to this point at this. So at t is equals to t2, this is here. This planet is at this position. So this line joining the center of to the sun. So this line joining center to the sun swept some area. This is the area swept. So if I take out this portion only, so this will look like this. A little curved path is there. है ना? So what we can do, we can assume the distance from the center of sun to the center of this planet to be small r. Okay. And this angle would be theta. Got it? We can assume that these point, let's say this point is A, this point is B. These points are too close to each other so that we can assume that this would be a straight line. The line joining the point A and B is a straight line. So what you will have? You will have a triangle. This would become a triangle. Okay. So if you are able to calculate the area of this triangle, what is that? The area of the triangle is what is the formula for area of triangle? It is half into Base into height. What is the base? Base is AB. Let's say the velocity of this planet at B is V, and the time taken by this planet to reach A is delta t. So we can say that the distance AB, what is the velocity? Velocity is change in distance divided by change in time. So we can say that S is equals to AB here. So AB is equals to V into delta t. Okay, got it? Now, and this is the hypotenuse of this triangle, this R, and this is the base. This is the base. Okay. Now base is AB. This is the height. So this AB is V delta t. Okay. So we can say that this area of this triangle is 1 by 2 times base, which is V into delta t, multiply what is this height? This height you can assume as, if this is R, this angle is theta. Sorry, the angle between this R vector and the velocity vector is theta. So we would resolve this R vector into two component. One of the component will come in this direction and one of the component will come in the perpendicular to B. Okay, got it? And in that thing, we will take the perpendicular component, because this r sine theta is nothing but the perpendicular component to V. So we will take r sine theta here. Okay. So you can say that this will become this is the area of this triangle. Area of triangle. If you take the change of this area of triangle per unit time, okay, if you take this and multiply this m by m, so what you will have? You will have delta A, which is the area of the triangle, divided by delta T is equals to 1 by 2 times V into delta T r sine theta m divided by delta T into m. So m and m got cancelled out. M we have to take here, and delta T will cancel out. You can see that this will become mvr sine theta, which is nothing but the angular momentum. So this delta A by delta T is equals to L vector by 2 times of mass, which is because this angular momentum is constant. So this whole expression, which is L vector divided by 2 into mass. Mass is a constant quantity. So this will be a constant value. So we have just proved this law, the Kepler's second law, which tells us that the aerial velocity is constant for each and every planet revolving around the sun, and which is equals to L vector by 2n. Okay. So if I just So you like this is the area L vector angular momentum, which is mr cross v. Here you will see the same triangle that we have considered. P is the linear momentum. L vector is r vector cross p. You can write it as if you put m inside. So the same thing that we have did, it is written here. Okay. So finally we have proved that the delta A by delta T is a constant quantity. Now the laws of period we have to take. Law of period. Law of period tells us about the period, time period to complete one revolution by a planet around the sun. So how this time period is proportional to what is the uh, time period of any planet? How does it affect? So it will tells us by this law, the law of period. So it tells us that the square of the time period of revolution of a planet around the sun is directly proportional to the cube of semi-major axis of the ellipse traced by the planet. In simple words, we can say that this is the semi-major axis, this axis is the major axis, complete major axis. This complete length is the major axis. This is major axis. And this half is the semi-major axis. Semi-major axis. Okay. Got it? So, according to the law of period, what does it tell us? That the square of the time period of revolution of a planet is proportional to the cube of semi-major axis of the ellipse traced out by the planet, which means t square is directly proportional to, if the major axis length is 2a, this length is 2a, the length of major axis, so half of it will be a semi-major axis. So you can say that square of the time period is directly proportional to the cube of semi-major axis. This is the law of period. So this is semi-major axis, which is a, you can see in the diagram. So t square is directly proportional to a cube. Okay. If we want to prove this law, so we would consider a circular orbit to prove this. Okay. A circular orbit we are using. We can also do it by a elliptical orbit, but it will take time. So we will doing by this assumption. Okay. So suppose this planet is revolving around this heavier planet with a velocity v. On, let's say this is a satellite. Okay. And the time period taken by this satellite to complete one revolution is capital T. And this length is small r from the center to the center. Okay. So what we can do, we can take that the here a force acting towards the center of the heavier object, which is the centripetal force Fc. And from that you can say that the centripetal force, which is mv s square in this case divided by r, is equals to the gravitational force. It is the same force Here the centripetal force is nothing special. Centripetal force is the force of gravitational attraction. Okay. So it is gm. Mass of this planet is, let's say, capital M, and this planet has a mass of small m. So g capital M small m divided by r square. So from that you can say here that v is nothing but square root of g capital M divided by r. Okay, we know that v is equals to distance upon time, and time taken to complete one revolution is t. Now what is the distance covered by this planet in one revolution? It is the circumference of this circular orbit, and circumference is nothing but 2 pi small r divided by t. From here you can say that t is nothing but 2 pi r divided by v. Okay. Now v here is nothing but vs. Put the value of vs from here to here. So you will have t is equals to 2 pi r divided by square root of g capital M by r. So the third place will go upside. You can say from here, this t is nothing but 2 pi small r square root of r divided by square root of g capital M. Now, take square of both sides. Of both side. So this is t square. 2 square will be 4. Pi will be pi square. It will become r square. Square root of will be vanish out. So it will become r divided by gm. Now, from this expression, you can say that t square is equals to 4 pi square r cube divided by the gm. So in this expression, this whole term, 4 pi capital G and capital M are the constant. So from that you can conclude that this t square is directly proportional to r cube. Okay, which is the distance from the center of the planet, and it satisfies that the period of revolution, the square of the period of revolution, is directly proportional to the distance of semi-major axis of the cube of the semi-major axis from the center of sun. Okay, but in this equation, this is the distance between the planet and the object. So it is satisfying the equation that t square is directly proportional to r cube. Okay, which means the square of the time period is directly proportional to the cube of distance between them. I hope you are clear with this. Now, there are some different time period are given for different planets in our solar system. Like for Mercury, if you will say the semi-major axis is 5.79, 5.79, 10 raised to the power 10 meter. Okay. For that, time taken by is 0.26 years, which means 0.24 year. Okay. So if you multiply this with 365, you have the exact idea that how many days the Mercury will take to complete one revolution. Okay, and it is nearly about 88 days or 84 days. Okay. Got it? And Mercury is the planet which complete its revolution faster than any other planet present in the solar system. Okay. So this ratio t square by a cube is 2.95. Our Earth, the distance is 15 into 10 raised to the power 10, which means 15 crore kilometer. 1 year it will take, the ratio will be 2.96. Okay. From here you can see that this ratio q, which is t square by a cube, is nearly constant. There is no so much of variation, and that is satisfying the Kepler's law of time period. 2.95, 3.00, 2.96, 2.98. It is nearly 3 for each and every planet. Okay? Which satisfy the constancy of time period, square of the time period with the distance of semi-major axis of the elliptical path that is traced by the planet. Okay? You can also see that the planet Pluto, which is excluded from nowadays, it is not the part of our solar system. So, but when it was, it has a distance of 590 times 10 raised to the power 10 meter, which is the farthest in our solar system. And it take about 248 years to complete one revolution about the sun. On this planet, all you will find is ice only. Okay? Because hardly sunlight will go there. Okay? There is no chance of life. Okay? Now, so this is the question from the law that we have studied. So this question I will read it for you. The Galileo measured the orbital sizes of Jupiter's moon, using the diameter of Jupiter as a unit of measure. He found that Io, the closest moon to Jupiter, LO you can say, had a period of 1.8 days, which means it revolves around the Jupiter. It complete one revolution around the Jupiter in 1.8 days and was 4.2 unit from the center of Jupiter. So we have in this question only Jupiter is at the center of the elliptical path of its moon. Okay, so we have taken Jupiter and its moon only. Now the Callisto, the fourth moon from the Jupiter, has a period of 16.7 days. Now using the same unit that Galileo used, predict the Callisto's distance from Jupiter. So I have given you 1 minute to solve this question. The formula that will apply in this question will be t square is directly proportional to aq. That is the formula we are going to use in this question. Try to solve this. Naresh, Hashira, Priyanka, Vikas, Bhavna. All of you guys try to solve this question. Okay. Time period is given for one. And distance is also given, which is 4.2 units. Okay. So you do not have to worry about its kilometer, meter or whatever. It mentions its units. Okay. So try to solve this question. Okay. Are you guys solving this question? Or let me just finish it with the solution. Okay. So here what we have given, the time period of LO, which is 1.8 days is given, and the time period of Callisto, this is given as 16.7 days. The distance, which is the 4.2 unit from Jupiter, is given as 4.2 units. Now, the distance of Callisto from Jupiter has been asked. So what we can do in this, you will see that T square is directly proportional to A cube. So what we can say, that T square is equals to some constant into A cube. For TIO, I am taking as T1. So T1 square is equals to KA1 square cube. And for Callisto, I am taking T2. So T2 is equals to KA2 cube. Now, if you take the ratio of it, T1 by T2 whole square is equals to A1 by A2 whole cube. The same thing we have did here. Now you know the value of T1, you know the value of T2, you know the value of A1, then you can find out the value of A2. It's just the calculation that we need. Okay. So this expression finally you will have. Okay. Put the data in it and you will have the answer as 18.54 unit, which means as the distance from the heavier mass object has increased, the time period of revolution is also increased. Okay. So this is the final answer to this question. Thank you so much, guys. The lecture has been over. If you want to ask something, if you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Okay. Thank you so much for being attentive in the lecture. Thank you so much. Bye bye. Take care.